Okay, thank you very much for kind introduction. Good afternoon, everyone. My name is Nakayama from Aichi Institute of Technology in Japan. It's not so famous as universities, but it is located at Toyota. Toyota is very famous because of automobile. Toyota, big company, is located at Toyota City. Yeah, but anyway, I would like to start a talk. Okay, excuse me. It doesn't work. I'm sorry. It's touching. A realistic Vortex model is required to investigate the actual particular characteristics of a vortex. And there are several vortex models have been proposed and applied for wide flow fields in nature or engineering. But because they are derived under specific conditions, they may not be suitable to realistic conditions. This is yes, I have described some vortex, Burgers, Rosenhead Burgers, or Q-vortex as asymmetric vortices, and as asymmetric vortices, Akita vortex or strategic vortex by Professor Moffat, Kida, and Okitani. And in the experiment, it is proposed by Batista or Wood, but it is, but they assume asymmetry or estimate azimuthal flow only. Okay, and on the other hand, in investigation of geometry of vertical flows, a local flow geometry using eigenvalues, eigenvector, or invariants of velocity gradient tensor has greatly contributed to investigate vertical flow classification, such as divergent or convergent vortices, or vortex definition or identification. It's very famous, delta or Q or lambda 2 or their unified definitions. And on the other hand, a quantity to specify flow symmetry of skewness has been required. But recently, some geometrical quantities to specify the symmetry or detailed feature of radial or azimuthal components has been derived. And they have classified that almost divergence convergent vortices, inflow or outflow vortices, ever analyzed by eigenvalue of the velocity gradient tensor has been found to have actually mixed inflow and outflow vortices. And this quantity at vortex center express primary characteristics of vertical flow in homogeneous isotropic turbulence. It was reported. And also interaction between vertical flow and the bundle of vorticity line have been found using these components, quantities. And they should be considered in the establishment of vortex model. So present our objective is to derive universal characteristics in the vertical flow structure and to clarify condition in radial, azimuthal, and axial flows derived from mathematical aspects and interaction with vorticity lines. Excuse me. Okay, first we introduce local flow geometry. A local flow of vector V field can be given by this equation, gradient tensor of vector V. And then in 3 dimensions, because it has at least one axis, that is one real eigenvalue and one real eigenvectors. So the local flow in the plane, non-parallel to the real eigenvectors, specifies vertical or non-vertical features. And the planar flow can be decomposed into radial and azimuthal component, and then can be expressed by specific coordinate forms divided by distance. So The feature of radial and azimuthal component can be given by eigenvalue and eigenvectors of their quadratic forms. Now we define a sorority as a geometrical average of eigenvalues of local azimuthal flows. So if sorority is positive, it indicates that the sign of two eigenvalues have the same sign. So azimuthal component has uniform direction, that is soaring or vertical flows. And because this geometrical average can be expressed by second invariant and real eigenvalue of the gradient tensor, so it is invariant independent of the plane. And similarly, we can define a solidity as a geometrical average of eigenvalues of local radial component. So if solidity is positive, then it indicates that local radial flow has the uniform direction. So it means complete inflow or complete outflow along the point. And if solidity is negative, then the radial flow has both inflow and outflow. And one more quantity is vertical flow symmetry. It can be given by the ratio of two eigenvalue of local azimuthal component. It is noted that this quantity influences the solidity. So if vertical flow symmetry is low, then the local radial component become to have both inflow and outflow. Okay. Okay, next. So now we apply the sorority to velocity field of the flow. In a vertical region where the sorority of the velocity is positive, then velocity gradient tensor become to have one real eigenvalues and complex conjugate eigenvalues, say epsilon r plus minus I phi v, and complex conjugate eigenvector with PL plus minus I eta PL, where the real part epsilon r is equal to average of eigenvalues of local radial flows here, and the imaginary part is equal to the sorority, that is geometrical average of two eigenvalues of local azimuthal component. So this is physical interpretation of complex eigenvalue of the velocity gradient tensor. And then local flow can be given by this equation, which indicates that flow swirls in a plane defined by xi PL and eta PL and proceed or converge along the real eigenvectors. So now we can define the swirl plane as the eigenplane defined by xi PL and eta PL. Here we define a vortex space, that is Galilei invariant coordinate systems associated with a swirl plane, where also normal bases are parallel to xi PL, eta PL, and their normal vectors. And it is noted that xi PL, eta PL can be set to be orthogonal. So vortex space has a feature that x check 1, 2 plane is identical to swirl plane, and also x check 1 and check 2 axis is identical to a long and short axis of elliptic vertical flow, asymmetric vertical flow. And in the vortex space, velocity gradient tensor can be represented by this form, which is composed of epsilon r and sorority and vertical flow symmetry, and also velocity vector component parallel to xi PL and eta PL. It indicates that all components are Galilei invariant. And And in the third plane, the eigenvalue of local azimuthal component can be given by minus lambda sorority and minus sorority divided by vertical force symmetry. And their eigenvector are identical to long-short axis of elliptic vertical flow. That is x check 1 and 2 axis. And about radial flow, the two eigenvalues can be expressed by this equation, composed of epsilon r vertical force symmetry and sorority. And the eigenvector of local azimuth flow lie midway of x check 1, 2 axis, just midway of a short and long axis of elliptical vertical flow. And about local azimuthal and radial component can be expressed by this equation when we express the coordinate component x as the radius r and angle theta from x check 1 axis counterclockwise. So this equation indicates that local radial and azimuthal component are periodic around a point, and given by wave number 2 and 0. And condition of uniform direction of radial flow, complete inflow and complete outflow, is given by the condition of positive sorority, which can be given by this inequality. So this inequality indicates that if swirling is intense or vertical force symmetry is low, then sorority become negative, and the radial flow become to have both inflow and outflow. So this is universal condition derived from local flow geometry. Radial and azimuthal flow has wave nature with wave number 0 and 2 around the point, and maximum and minimum radial flow areas lie midway of long-short elliptic axis, and a feature of the radial component depend on epsilon r and sorority and vertical force symmetry. So it is noted that before epsilon r has been applied to classify inflow vortices or outflow vortices, but it actually most of vortices have both inflow and outflow. So epsilon r is not appropriate to classify the vertical flow features. And about actual flow, because velocity gradient tensor in vortex space indicates that the gradient of actual flow is 0 in the third plane. So the local actual flow can be expressed by its Hess matrix, Hessians. So local actual flow can be expressed by this equation. And then similarly, if we express the coordinate component in terms of radial r and angle of eigenvector of the Hessian, it can be written by these equations. So similar to local radial and azimuthal flow, the actual flow also has wave number 0 and 2. Okay. Before we analyze vertical flow structure, we would like to talk about one more thing. That is just interaction between vertical flow and bundle of vorticity lines. this is vortex equation, and vortex stretching is expressed by S omega, where S is the rate of strength tensor and rate of strength tensor. And in vortex space, rate of strength tensor is expressed by this equation. And it is noted that, please note that it includes omega 1 and 2 components. So then vortex stretch term S omega is given by this equation. It indicates that vortex stretching swirls vortex T vector. It's very strange because a rate of strength tensor is unitary. It's never rotate. But in vortex space or in vertical region, it has nonlinear effect actually. So then in the vertical region, vortex stretching rotate or swirls a vortex vector. So the swirling, yes, swirlity of this rate of strength tensor is just equal to the swirlity of velocity. So, but this case indicates that it swirls vortex T vector space, not in the physical or flow space. So we may wonder how does it swirl in vertical regions? Yes, it has conditions. So now here we localize the vortex vector, localize and decompose into radial, azimuthal, and normal component axis directions. Then the vortex stretching is expressed by these equations. And if rate of strength tensor, modified rate of strength tensor swirls the vector about half pi, then a component S omega r determines the rotate direction. Because this is one example where omega r has a feature of complete outflow. If it has complete outflow feature, it is turned counterclockwise. So S omega r becomes to swirl counterclockwise. And on the other hand, if omega r has complete inflow features, so all radial component is changed to turn or swirl clockwise. So if vortex vector swirl or not depends on the feature of radial component of vortex T vectors. And its feature is given by source T of the gradient tensor of vortex vector. And then about between axial component and vortex vectors, a rotation of vortex vector has a relation expressed by this equation. That is, minus Laplacian of axial flow is identical to the third component of rotation of vortex vector. And if the Laplacian associated with the subplane is dominant, then this equation can be expressed by this equation. And then the left-hand side term indicates is given by the Hessian of axial flow in the swirl plane. So then the rotating feature of vortex T vector in the swirl plane determine or specify the feature of the axial flow. So this equation indicated the local azimuth component of vortex vector given by the quadratic forms. So in the interaction of vortex line to vertical flow, So vorticity line with swirling. Swirling vorticity line operates to generate an actual flow. So when vorticity vector swirls, then it should have complete inflow feature of radial component of vorticity vector. Okay, now we show analysis and an example of vertical flow in a homogeneous isotropic turbulence analyzed by pseudospectral method with low Taylor Reynolds number about 36 and Kolmogorov length is about 0.012. And the vortex is identify the swirlity of the velocity, and vortex center is identify the local maximum point of the swirlity. And then after its center is identified, then vortex space is defined in this vortex center. Okay, this figure shows one vertical region and one swirl plane and vertical flow. And these two figures shows the decomposed radial and azimuthal flow in the swirl plane. And white line indicate product curves of local azimuthal and radial components. And about azimuthal flow, it indicates the flow is elliptic, and its feature is represented by the coordinate curves of local azimuthal component. And about the radial flow, it has both inflow and outflow, and its area is represented by the coordinate curves of local and radial component. Okay, this figure shows the distribution of azimuthal flow around the vortex center at several radii, from 0.25 ether to 2 ethers. And the dotted line indicate a coordinate curve of local azimuthal component. So this figure shows that azimuthal flow expand along the as the radius increase, and its distribution is completely according to the coordinate curve of the local azimuthal component. And this figure shows the spectra of these distributions. It shows that the Fourier coefficient of k equals 0 component and k equals 2 component are dominant. So it indicates that local flow geometry gives its primary characteristics. And similarly, this figure shows the distribution of radial flows. So it has both inflow and outflow because it has, and then the negative area is more because it is average inflow vortices. So similarly, as the radius increase, the radial flow expand, and its distribution is completely according to the coordinate curve of local radial component. And this spectra similarly indicate the component at k equals 0 and 2 are dominant. So it is identical to the feature of local flow geometry. Similarly, this figure shows the distribution of axial flow of one vortex. And dotted line indicate the coordinate curve of the Hessian of the axial flow. It's also identical to the axial flow distributions. And the Fourier spectra indicate that coefficient at k equals 0 and 2 are dominant. So local flow feature capture the primary characteristics of actual finite scale vortices. And by the way, this figure shows one vertical region and swirl plane and the bundle of vorticity lines where vorticity line swirls. And then when the vertical flow vorticity line swirls, according to its direction of swirling, here the axial flow is generated downwards. And it's very interesting because pressure gradient has a direction upward. However, axial flow is generated downward. It indicates that, of course, there is effect of a pressure gradient, but however, the effect or influence of swirling or vorticity vector is dominant for the generation of axial flow. So this figure indicates joint probability density function of Hessian of the axial flow and eigenvalue of local azimuthal component of vorticity vector. So it has very high correlation, about 0.9. And this figure shows JPDF with the angle of eigenvalue of local azimuthal component and the Hessian, eigenvector of Hessian of the axial flow. They also have strong correlations. So this is the equation of axial flow given by the Hessian of it. But its Hessian or its angle of eigenvector can be replaced by the eigenvalue or eigenvector or local azimuthal flow. Okay, as a future investigation, it must have more complicated or unknown physical feature in the vortex core region. And this three figure shows the vertical region, swirl plane, and bundle of vorticity line, and the pressure minimum line followed by normal vector to pressure minimum plane derived by vertical flow. And this is a bundle of eigenvertical axis line followed by local vertical axis, that is real eigenvector of velocity gradient tensor. This is the same to the vector of Vortex. So three bundles have three geometrical characteristics. So it shows us unknown or unique characteristics of a vortex. So investigation of its mechanism reveals what happened in the core region vortex. It should have unknown physical aspects. And this is one example of investigation of bundle of axis lines as an example of pressure minimum lines. Here, a pressure minimum line swirls. A pressure minimum line also even swirls. And this vector field indicates the vector of normal to pressure minimum plane. Generally, when we consider the pressure minimum, we check the contour. But if we check the bundle of it, we can find that pressure minimum plane also swirls. So geometrical analysis of the axis line provides useful information that a contour of pressure minimum cannot indicate. Okay, and then I would like to. It is noted that this is second Hessian of pressure in the swirl plane, derived from vertical flow. Lambda 2 definition is very famous and applied in many fields, but this is similar but different because lambda 2 definition indicates the Hessian or pressure minimum plane but it is different from Hessian in the swirl plane. So if we check the Hessian or pressure by the vertical flow, we should check the Hessian in the swirl plane, not pressure medium plane. So this figure shows the contour of the Hessian or the pressure in swirl plane. So it is somewhat different. Okay, so this investigation indicates the pressure minimum plane may have the feature of helicoid, but it is under investigation. Okay, it's a conclusion. A universal vertical flow structure in terms of the local flow geometry indicates that radial and azimuthal and axial flow has a wave feature of wave number 0 and 2, and radial azimuthal flow is periodic. Maximum and minimum radial flow area right midway between long and short axis of elliptic vertical flow. And radial flow feature depend on swirlity, vertical flow symmetry, and may have both inflow and outflow according to their values. And axial flow can be expressed by coordinate curve of Hessian in the swirl plane, and its Hessian and its direction is deeply associated with a swirling or vorticity lines. And then any asymmetric vertical flow feature can be expressed by swirlity, vertical flow symmetry, and average radial flow intensity, that is epsilon r. So a realistic vortex model with finite scale may be established with these characteristics as a fundamental feature. Okay, thank you very much for your kind attention.